Thank you so much for staying to the last session. So this project was developed under the curiosity to understand how triple-negative breast cancer is prevalent in African American women. It's very aggressive and very difficult to treat. Disparities in triple-negative breast cancers are multifactorial. There hasn't been one single gene that has been associated with triple-negative breast cancer. It's multifactorial, and we want to understand how the environment is contributing to triple-negative breast cancer. And so the large question here is, could chemical exposure disparity lead to triple-negative breast cancer to be more prevalent in African-American women? Today we're just going to be able to answer part of that question. So the first aim is to characterize chemical exposure differences by race in the U.S. population using an expose-and-wise screening approach. In addition, we can expand this project further to the entire NHANES population, quantifying chemical exposure differences by race, gender, socioeconomic status, and smoking habits. You can imagine this is a lot of data that's going to be generated, so here we're going to develop a visualization technique to visualize all these exposure patterns by these different demographic features across a broad set of chemical. So we're using the NHANES population for 1999 to 2014 for the chemical and demographic databases. There's 74,000 participants in here. So here's the breakdown by sex. You see that it's evenly distributed by sex. And then here's the breakdown by race. One thing to note here is that Mexican Americans and non-Hispanic blacks are oversampled by a factor of 2. Okay, so what are the steps needed to undergo this project? So there's about 200 individual files to gather, and so I developed an algorithm to compile all these files into one large database of 82,000 participants and 550 biomarkers. And then we need to do some cleaning to prepare for the analysis. There's certain chemicals where it has 2 different NHANES code names, and so that had to be harmonized for consistency. We had to exclude about 7,000 participants because they just didn't have measurements for chemicals. And then we had to exclude biomarkers that are not indicative of a chemical exposure, so biomarkers like selenium, which is indicative of dietary habits, had to be excluded because that's outside the scope of this project. There's certain lipophilic chemicals that have 2 types of measurements, one that considers adjustment for lipid, one that didn't. We took the measurements that consider lipid adjustment because you can imagine participants with higher blood lipid would tend to have higher lipid chemicals, and so that had to be adjusted accordingly. And then we excluded chemicals that have a detection rate below 50%. And so this leads to having left 75,000 participants and 144 chemical biomarkers. So here are the 144 biomarkers stratified by the different chemical classes. So here we are at the analysis, and so we do a multivariate linear regression, log 10 transforming the chemical concentration to meet the assumption of normality. Our main predictors are race here, with the reference being non-Hispanic white, and another main predictor is gender, the reference being male. And then here we have probably income ratio to use as a surrogate for socioeconomic status. And so if your probability income ratio is higher, you have a higher socioeconomic status. Here we also use cotinine as a biomarker of smoking. And so we took these betas and did 10 raise the beta to have a fold change. And for protein income ratio and cotinine, this is a continuous variable, so what we did was we compared the chemical exposure differences with those in the 75th percentile protein income ratio and those in the 25th percentile protein income ratio. And we did the same thing for cotinine. So you can imagine there's a lot of data being generated, and so I play this game where I give myself just one graph to display all the message that I want to, and so that's led to the advent of the alphabet soup plot. And so here I show, so let's try to break this down and try to read it. So the chemical classes are indicated by the different colors. The demographic comparisons are indicated by a letter. So here protein income ratio is indicated, it starts with a P, so I denote that as a P, comparing the 75th percentile and the 25th percentile. Smoking here is denoted by ESC, where I compare again the 75th percentile and the 25th percentile. G stands for gender, comparing female versus male. And then the races are M, to denote Mexican Americans compared to non-Hispanic white. H here is used to compare Hispanic versus non-Hispanic white. Here black, B is for non-Hispanic black, and other race is denoted by O. And other race consists of Asians, Muslims, and participants of multiracial background. Okay, so one thing to note here is that, so let me try to read this. So here we have an S, and so that denotes smoking, and here it corresponds to NNAL, and so this is saying that those who are in the 75th percentile of codeine levels, they have 10 times as much NaNL in their blood compared to those who are in the 25th percentile. And then here I'm going to highlight all the S's, and you note that these chemicals here are VOCs, PAHs, and a smoking-related compound, NaNL. And so this was a good sanity check because we know that smoking is highly associated with these type of compounds. And so I'm going to now remove the smoking so that we can focus on the other demographic comparisons. So there's 3 regions here. So there's one region over here. This denotes where the chemical is of higher concentration, those of higher socioeconomic status. It's also higher in females and those of Mexican, other Hispanic, Black, and other races. And then on the opposite side, these chemicals are of higher concentration in those of lower socioeconomic status, male, and in non-Hispanic white. And then in the middle here, these chemicals don't show that high disparities across these different demographic features. So there's a lot of stories to tell here, but we're going to try to answer that questions of exposure disparities by race and woman. So we're just going to focus on the top 20 chemicals. So you see right here that propylparaben and methylparaben are on this N, and it's of higher concentration in female versus male. And so here, this G up here dictates that it's 6 times higher in female compared to male for propylparaben, and then for methylparaben, it is 4 times higher in female compared to male. And then next we're going to look at B stand to denote the comparison between non-Hispanic Black and non-Hispanic white, and we see that it's 3 times as much, on average 3 times as much in non-Hispanic Black compared to non-Hispanic white for both methyl and propylparaben. Okay, so here comes the cooler part where this is from the interpretation from my mentor, Olivia Joliet, where if we do a stratified analysis by gender, particularly in women, we expect that non-Hispanic Black women would have the highest concentration compared to the other race. And so Adam Kahana, who is an undergrad of Dr. Justin Colacino, who's my co-mentor, did this analysis in women's. And so now we're gonna look at the top 20. And then, so I said that in the overall alphabet zoo plot, the African American woman would be higher compared to the other race. And it's confirmed here when we looked at methylparaben and propylparaben, B being the highest compared to the other race. Okay, so with that, in summary, so we show relative magnitude of disparities of chemical biomarkers across the multiple classes using this plot, and it's a tool where we can start to identify which combination of chemicals and population are prone to high exposure, and this would help to prioritize them for further evaluation to look at their health outcomes. And it's also a tool to inform which subpopulation with a combination of demographic factors are at risk for high exposure, as we saw with the example of non-Hispanic Black women being a high exposure for parabens. And so here, these exposure patterns are well known, and so, but we want to develop a visualization where we can compare all these widespread exposure across different chemicals, across different demographic features. And so I want to emphasize that here I just quantify exposure patterns across these features. We did not link them to breast cancer yet, and so Justin Colacino has a wet lab portion where my lab mates in that portion will conduct data-driven experiments to understand how chemical exposure can lead to breast cancer. And so with that, I'd like to thank my mentor, Justin Colicino and Olivier Joliet, for their patience and encouragement over the years, and I'd like to thank my teammates from both labs for the help on this project. And here's our funding, and thank you so much for staying on the last day and listening to my presentation.